general relativity step by step. Metric tensor, incredibly important in relativity, and I'm going to show how it's used in this screencast, or maybe I'll take 3 or 4 separate screencasts over it. So I'm going to set up a general curvilinear coordinate system here. If I can, here we go. So here's some lines of some contours, some coordinate lines here, and you'll see that they're all horrible. 1, x1 equals 2, x1 equals 3, and so forth. And if I change to blue, we're going to have some blue contour lines, and they're going to be terrible as well. They're going to be terrible here. And that's x2 equals 1, x2 equals 3, x2 equals 4, and so on. If I want to talk about the length of a vector, if I've got a point here, P, P1 let's say, and there's a point here, P2, and I want to work out how long that vector is, that's a vector V, which takes you from point P1 to point P2, then the length of the vector is problematic. There are ways around it that we can see, but for the moment I just want to observe that this length of this vector, as it's cruising through this space here described by these red and blue coordinate systems, sort of this nice arrow here, the lines are changing. The blue lines are getting further apart and closer together, and the red lines are as well, and they're changing in direction. So the length of the vector, as you kind of cruise up here, you're changing your speed, you're changing your velocity, as measured in the curvilinear coordinate system. So the length of a vector is problematic. So I'm just going to consider small vectors. So I'm going to consider vector v equals delta x1 e1 plus delta x2 e2 plus delta x3 e3, just a 3-dimensional coordinate system, where delta xi is small enough to neglect terms of second order and above. Okay? So I'm going to do that, and I'm going to do it properly mathematically in the next screencast. So I'm going to stop there.